All right, welcome everyone. The goal of this video is to go through the topics that I'm going to cover more exhaustively in the videos that follow more quickly. So this is like a greatest hits of matrices in R. So if you're familiar with matrices and matrix arithmetic, you've taken a course in linear algebra, you may be able to watch this video and just get caught up pretty quickly with how to do matrix operations in R. If you are not familiar with matrices, then I don't think this video is going to be a great coverage of these topics. And I would encourage you to watch the videos that follow that go into this in much more detail. So when we're working with matrices in R, all of these commands that I'm going to go through, these are all in base R. So you don't need to install any packages to run any of these code cells. So first, if I want to enter a matrix and store it in R, then the main function for doing that is the matrix function. And the matrix function takes one argument, which is a vector of data. In this case, our vector is the integers from 1 up to and including 10. And then we can specify the number of rows and the number of columns that we want our matrix to have. So here I'm going to arrange the 10 first integers into a matrix that has 5 rows and 2 columns. And so running this code cell gives me the output that I can see below. And what you might notice here is that we've got these 10 values, and rather than fill them in as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This filled in the values first down the first column. So it first completed column 1, and then it goes and fills in the rest of the values in column 2, and it would keep going based on the number of values and the dimensions of your matrix. And I also want to just note that here it's a little bit redundant. I don't need to enter both the number of rows and the number of columns, since if I have 10 values arranged in 5 rows, R will know that that needs 2 columns. So if I deleted that last argument, I get the same matrix back. But one thing that is worth pointing out is there is a by row argument, which we can set equal to true. The default is it sets this argument equal to false. But if I set this equal to true, this is going to fill in the values across each row. So the first row will be filled in with 1, 2, and then it goes to the next row for 3, 4, and so on. So I'll run this and you can see the difference in how the values are filled in the matrix. So by row equals true means we go across each row. Deleting this option fills in the values down each column. So that's the main way that we can define matrices in R using this matrix function. And I want to also just point out here, I've just displayed the matrix A on screen, and it tells us that A is the data structure is a matrix. It's 5 by 2, and that all of the values in my matrix are integers. So a matrix can only have a single data type. In this case, they're all integers, and we can print it out using the print command, and the output looks a little bit different. It tells us the row indices and the column indices for the matrix. Another popular way to construct matrices in R is using row and column binding functions. The column bind function is cbind. The row bind function is rbind. And this is useful if you've already got vectors that are defined, or maybe you're extracting columns from a data frame, and then you want to merge those columns and create a vector, a matrix of some sorts. So in this case, let's say we've got vectors 1 and vector 2, vec1 and vec2 that I define in this first code cell. These are now one-dimensional objects. So this is vector 1, and this 5, 6, 7, and 5, 6, 7, 8 is vector 2. If I do cbind on these two vectors, vec1 and vec2, it's going to bind them together as two columns of a matrix. So it uses this first vector, vec1, 1, 2, 3, 4, to fill in the first column of the matrix, and then it uses vec2, which is 5, 6, 7, and 8, to create a second column of the matrix. So this is going to create a matrix where each column is one of these vectors in the cbind function. And similarly, we could do an rbind with these vectors, and that's going to merge these vectors together as rows. So rbind is going to set vec1 to be row1, and it's going to set vec2 to be row2, and that gives me a matrix with 2 rows. I can run this and double check that. So that's how we can, another way that we can create matrices if we've already got some vectors that we want to bind together. When we want to find the size of a matrix, how many rows and how many columns are in the matrix, let's consider this matrix A, which is a 5 by 2 matrix. If I run the dimension function dim on A, it tells me it returns a vector of 5 rows. The first number tells me the number of rows, and the second number tells me the number of columns. And this is being stored as a vector. So this is 2 values in a vector. So if I want to get just the number of rows, then what I can do is pull off the first element of the output that I get when I run dimension A, and that would give me the 5. And if I want to get just the number of columns, then I can say dim A and then extract the second element of that output, which would be the number of columns 2. If I try and calculate the dimension of a one-dimensional vector, if I use the dim function on that, I get a null output, and that's because this function expects a matrix as an input, a two-dimensional matrix, and not a one-dimensional vector. We can also get the number of rows and columns from a matrix using the functions nrow and ncol. So nrow A tells me there's 5 rows, ncol A tells me that there are 2 columns, and this is just an alternate way instead of using the dim function. To create an identity matrix, next up in our greatest hits, if I want to create an identity matrix, an n by n identity matrix, I can quickly do that. I don't need to use the matrix function. I can use a function in R called diag, and I just enter the number of rows and columns I want in my identity matrix. So if I want a 3 by 3 identity matrix, I do diag 3. If I want a 9 by 9 if I want a 3 by 3 identity matrix, I do diag 3. If I want the 9 by 9 identity matrix, I do diag 9, and that gives me identity matrix. All of the diagonal entries are 1. All of the off-diagonal entries are 0. So that's how we can more quickly create identity matrices in R. I'm not going to cover indexing and subsetting in this kind of greatest hits tour. I will encourage you to watch the specific video that covers this content because it is a little bit more involved. So I'm going to skip over all of these examples. That stuff is really important. So I want you to focus entirely on that stuff in those videos. But matrix operations, we can do that pretty quickly in this tour. So if I got a matrix A over here, which is 2 by 3, I define a matrix B, which is also 2 by 3. Then recall we can add 2 matrices. We just add them component-wise. And the only way that we can add 2 matrices is if they have the same exact size, the same number of rows, and the same number of columns. And here I add 2 matrices just using the regular plus operator. So we add them just like we would add 2 numbers, and we can subtract those matrices using the subtraction operator as well. So you can verify the outputs here are performing matrix addition and subtraction correctly if I have a matrix of a different size. So if I try and take a 2 by 3 matrix A and add it with a different sized matrix, a 3 by 4 matrix C in this case, then this is what the output looks like when we try and add two matrices that don't have sizes that line up. So this is an undefined operation, and that's what that error message is telling us in R. If we want to multiply a matrix by a scalar, here, let me define this matrix A. And if I want to calculate 2 times a scalar multiplication, then I just do 2, and I use the regular multiplication operator times A. So that's going to multiply every element of matrix A by the scalar 2, and we can see that output down below. When we want to multiply two matrices, I'm going to assume if you're watching this quickly, you know how to multiply two matrices. And if you are not familiar with how that goes, then please watch the video that goes into this in more detail. But if you're familiar with how to multiply two matrices, then here is an example where we have a 2 by 3 matrix A, a 3 by 5 matrix B, and a 2 by 3 matrix C. So I can multiply matrix A and B because A has 3 columns and B has 3 rows. So when we have the number of columns of the matrix on the left is equal to the number of rows that we're multiplying on the right, then that matrix is going to be, that multiplication, that product is going to be defined. So I'm going to run these code cells to first enter matrices A, B, and C. And then in these code cells down below, I'm going to multiply them. And when we multiply two matrices in R, we do not use the regular multiplication operator. We'll see what that does if we try and apply that to two matrices. For the specific operation of matrix multiplication, which is a slightly convoluted operation. So it's important, if you're not familiar with how that goes, to watch that more carefully. But that would be the percent, asterisk, percent symbols together. These three denote matrix multiplication. So after I've entered A and B, if I want to calculate their product, I do A percent, asterisk, percent. This is matrix multiplication B. And this gives me the output, and it's great to practice this matrix multiplication by hand to check your work. A and C, those do not have dimensions that will allow us to multiply them. So A and C have the same number of dimensions. A has 3 columns. C has 2 rows. So that product doesn't make sense. And if you try and run that command, it gives you an error message similar to the message for when we tried to add two matrices of different sizes. And so if you were to try and use the wrong symbol, again, remember matrix multiplication is percent, asterisk, percent. If I just use the asterisk for the regular multiplication symbol, in general, if I tried to multiply matrix, multiply A and C, that gives me an undefined result, as we just said. If I use the asterisk to apply this multiplication, I actually don't get an error message. I get some output that looks like this. And what operation this is doing is it's performing element-wise multiplication. So if you've never seen this, that makes sense because this is not really a common way, a common operation for two matrices, but there is a way to multiply element-wise two matrices that have exactly the same size. And it's like addition, but instead of adding the elements component-wise, we now multiply them. And that we can do with the regular multiplication operator, but keep in mind, this is not matrix multiplication. This is some other type of multiplication called element-wise multiplication. that is denoted with this math symbol, the open dot circle. So this is a different type of multiplication than the default matrix multiplication. And a couple last things that I want to mention in this video. If I have a matrix A, and maybe I'll define it from this one over here, and I want to calculate its transpose, excuse me. So if I have this matrix A and I want to calculate the transpose, to calculate the transpose of a matrix in R, we use the t lowercase t function. So t of A gives me the transpose of matrix A above. If I want to find the inverse of a matrix, you can watch the video that explains how this function works a little bit better. But here I'm going to run this code cell to enter some matrix A. And if I want to calculate the inverse of that matrix, the function that I can use is solve A. So solve A actually computes the inverse of matrix A. And here I've stored it to A dot in for the inverse of A. And you can check these products below to make sure that when I multiply A and its inverse, I get the identity matrix back. Here, I've done that as well. It might seem, excuse me, that this is not the identity matrix, but in fact, it's doing a numerical approximation. So this is approximately equal to the identity matrix. The diagonal entries are 1, and this is all scientific notation. So these numbers mean this decimal times 10 raised to the minus 16. So this is like 0.0 with lots and lots of zeros. So this is essentially equal to 0. So both of these products check out, and this solve function does indeed, when a matrix is invertible, it will compute the inverse matrix. And last couple of operations. If I have a matrix A, there is a determinant function in base R, which is det. So I could take the determinant of A, and that happens to be 1 in this case. If I want to find the trace of a matrix, the trace is the sum of the diagonal entries. I can do that in a series of 2 steps. This function diag A is going to create a vector that contains all of the diagonal entries of a matrix if it's square. So we have a square 3x3 matrix. That function would create a vector of 2, 0, and 3. And then the sum function applied to that vector adds up all of the elements in the vector. So it would be 2 plus 0 plus 3, and that gives us the trace of 5. To find eigenvalues and eigenvectors, we can use the eigen function. This is also in base R. So when I run eigen A, and here I'm going to store it to some object I call EV, and I'm going to print that out down below. It tells me the 3 eigenvalues of this matrix. And for each of these eigenvalues, it also gives me an orthonormal vector, or at least it gives me, excuse me, a unit vector for that, a unit eigenvector for that eigenvalue, excuse me. So this is an eigenvector for the first eigenvalue. Column 2 is the eigenvector for the second eigenvalue. This column 3 is the eigenvector for this third eigenvalue. And moreover, this matrix of eigenvectors, each of the rows has unit length, each of the columns has unit length, and each of the columns are orthogonal with the other columns. So I can use this matrix to diagonalize the original matrix A. All of this stuff down here in this matrix is what we typically call the matrix P when we're diagonalizing it. So I can extract this vector, this matrix of eigenvectors using EV $ vectors. That pulls off just the matrix part down here. And then I can use this matrix that I'll store in P to diagonalize matrix A. So now by multiplying by this matrix P, the inverse of P on the left, and matrix P on the right of A, this diagonalizes A. And now we can see that the diagonal entries are the three eigenvalues that we got from this output. And all of these other values, they don't print out as 0, but they have e to the large negative value. So all of these off diagonal values are actually approximately 0. So these are all zeros. There's just some numeric approximation going on. It's doing things numerically with these functions. So that is a quick recap of the greatest hits of linear algebra in R.